Hi guys. So I want to look at the solutions for the homework on using recurrence relation counting problems. So this is still basically 8.2, right? And I agree that this is perhaps the hardest of the whole of 8.2 in the sense that it's not just solving the recurrence relation that by now you hopefully you know how to do, it's setting it up. And of course, if you cannot set it up, then how can you solve it? And the first one that I will cover, 45, is perhaps even, I must admit, I had to think a little bit about it myself. It's not, these things are not so easy anymore. So let's quickly review what is happening here. We have these genetically engineered species of rabbits, and they come in pairs. And a pair is always a female and a male, obviously. And so they are so well engineered that after 1 month, so let's how do you how do you attack this? Well, you start with looking at the first few how it starts. Look at the beginning, the so-called initial conditions, which we at some point need to calculate anyway. So, but the question is how to set this up, and that is perhaps the hardest. Now, if you look at this thing, let me read it. So we have after a pair of rabbits is if a pair of rabbits is 1 month old, it produces 2 new pairs. If it's 2 or more years old, then it produces 6 new pairs. So that's the problem, is that there's a difference. There's going to be therefore 3 types of rabbits. Okay, and so that's at least how I analyze it. You might have done it differently. I would say there are the new ones. So these are the ones of age 0. They are just put there, right? They are the newly born ones. Then there are the ones of age 1. These are the ones that have been there for 1 month. And then there are the ones that are of age at least 2. So how does it start? So n will be counting the number of months that have passed. So when no months have passed yet, what has happened, we put a pair newborns onto that island. One newborn pair. Oh, sorry, one new pair. Sorry, I sometimes get confused by the word pair. But it's, so these are, what I'm going to write down here is always the number of pairs. I'm always counting in pairs. So there's 1 pair. And then of course nothing of these 2 are 0 yet. Okay, what happens after 1 month? Well, what happens, of course, is that the first pair has celebrates its anniversary, its first month anniversary. So they become now 1 year old, 1 month old. Sorry, there's still none of 0 months old. There's 0 of 2 months or older, but there are new ones. The newly born ones come from that 1 pair that we have, and they produce 2 new ones. Okay. Now, is this, you might say, okay, what do we do with these numbers? What is it that we really want to know is the total, right? How many are there of all these possible ages? So we divide the ages in age 0, age 1, and age at least 2. Okay, you can say newborn, adolescence, and mature, if you want to put nice words on it. So, okay, the total, of course, is just the sum of these. So there's 1 here, at this moment there's 3 there. So things start happening more interesting in the 1 month later. Of course, now 1 month later, everybody gets 1 month older, right? So that means that these 2 will become 2, will go here, and these 1 go there, right? That's what happens. But now each of these, the ones that we have already, how many did we have already? We have already 3 of those, right? So that's the 3 that I'm now talking about. Yeah, so perhaps let me keep colors here. So the black ones are the ones that I already have. And how many do they produce? Well, that's there are new ones. I'm going to put them in green here. It depends a bit on who their parents are. If their parents is this pair here, then we get 6 new ones. If their parents are these guys, there are 2. Then each of them produces 2. So you get plus 2 times 2. Okay? So this means how many then? How many new do we get? 10 new. Okay, let me go back to black here for that one. So that is 10 new. So how much have we in total? 30. Okay, so let's go one more further. I mean, we don't need this many initial conditions. Well, we don't know yet, but we'll see. That's what all we need. But let's keep going and see what happens and to understand the mechanism. So somehow, well, we have in this a month ago. So we are now month 3. A month ago we had 13. Now these 13, of course, are still there. Where are they? Well, they're all now. These two guys have become all age 2 or higher. They have matured. Then these guys, they have now become 1 month old, so they go there. Okay, so we get again this shift, right? These two go there, these goes there, and then there are the newborns. How many? Well, there are 3 mature pairs, and they all produce 6 new pairs. And there are 10 adolescents who each produce 2 pairs. So in total we get 18 plus 20 is 38. Of age 0, newborn pairs, right? It's always in pairs. So 38 plus 10, 48 plus 3 is 51. Okay, so we could do one more if you not see what goes on, but it's kind of clear, right? How many are there gonna be here? Well, these are gonna be the ones that are at least 1. In this, let's concentrate on this. How many are gonna be there? Well, that is gonna be the ones that already have mature and the adolescents together. Okay, now that's 13, right? So there were 13 new ones here, these 10 plus these 3. Notice that is also the number of pairs that we had 2 months ago, right? Exactly. When are you more than at least 2 months old? Well, when you were born at least 2 months ago. And 2 months ago there were 13 rabbits running around. So for sure, some of them were very newly born. So it's only after 2 months that we are sure that all of those have now become at least age 2. Okay, how many do you think will there be of age 1? That's a little bit trickier, right? So perhaps it's easier to think about how many would there be if you put, I don't know how to do. I'm still here in month 4. So this is month 4. I want to calculate the number of total of age at least 1 or more. That's so in other words, the sum of these. So I want to calculate the sum of these two. Why do I say this? I know exactly what that is. How many are there? They have at least age 1. Well, as many as there were a month ago. This number. So this is the 51 that we see here. Okay. So this helps us a little bit understanding how these numbers are related. Remember, it will be the AN, right? These 3 intermediate numbers, you could give them names and try to work out equations for them, but I'm kind of trying to solve it without referring to giving special names to the 3 other ones. Because you see, what I'm trying to say is these numbers of AN, they come here. So this would be a 0, A1, A2, A3. This would be A4. But you see, part of A4 will be this 51 will be part of it. There's the 13 is also part of it. Of course, then we also know what this is, right? Because it's just the difference between these two. So the only kind of thing we have to really think about is what is this? Okay, but we know how to calculate that. That will be, well, we know we have to look at how many of mature ones that they will have to multiply them with 6. And then the ones of the adolescents, we will multiply with 2 and add them up. That will give us the newborn ones. So let me try now to write this up a little bit nicer. So let's start with the ones, how many are there of age at least 2? Okay, let's start with that. That one was something that if you just think about it, when are you at least 2 months old? When you were born 2 months ago or before that. So in other words, these are as many as there were 2 months ago, and minus 2. So this is the number of, so what I'm trying to say is in month n, I'm going to write down how many are there of age at least 2, an minus 2. Now, as I said, it is easier to think about how many there are at age at least 1, because then we can do the exact same reasoning. So the exact same reasoning tells of age at least 1, when you're at least 1 more old, is when you were born a month ago or before that. So an minus 1. Okay. So now we need to know how many are there of age 0. That's really what we need to know, right? Well, we actually also need to know how many there are of age 1. So let's calculate the ones of age exactly 1. Well, we discussed this, right? So how would we calculate this? This is the number of at least 1 month old. This is the one of at least 2 months old. So that would be the difference. So here it would be 51 minus 13, which is 38. So we can write this out. This would be the number of an minus 1 minus an minus 2. You agree? Because these are the ones at least 1 month old. These are the ones at least 2 months old. So the difference is exactly the ones of... Oh, sorry, I'm writing it wrong. So this is h1. Let me write it here. Okay. And then now comes the whole thing. How many are there of age 0? Oh, but that one is now not bad. I have to just look at the adults. How many adults were there? This many. And I know each of them produces 6. That's the product rule. So I get 6an minus 2. And then I have to look at the adolescents. Now be careful. Adolescence is given here. And each of them produces 2. So I multiply that number by 2. Okay. Good. So I know now exactly at month end how many there are of at least 2 months old, so how many adults there are, how many adolescents there are, and how many newborns there are. So now I can put it all together. How many are there in total? Well, there are the newborns. So let me work this out a little bit, right? It is 6an minus 2 plus 2an minus 1 minus 2 times an minus 2. That is, I'm going to write the n minus 1 first. Remember, we always prefer to write it that way. And then we have plus 4an minus 2. Okay. So what is an? Well, an are the new ones. So let's write them. An minus 1 plus 4an minus 2. And what then? And then the ones of age 1. And then the one of age at least 2. Well, I can make that simple and say, and then all the ones of age at least 1. So we have the newborns plus the ones that have age at least 1, that is this number, an minus 1. So we finally see that our recurrence relation is 3 times an minus 1 plus 4 times an minus 2. Okay. Yeah, granted, it's not so obvious that this is the case, that these are the exact recurrence relation. It takes a little bit thinking, a little bit working. You can now also check. Let's check here whether we can calculate that this number comes out here. So according to this, it should have been, so 51 should be 3 times the previous number, so 3 times 13, plus 4 times the one even before that. So this is the 13, and this would be 4 times 3. So is that correct? Is that 39 plus 12? It's correct. So at least that seems a good thing, that at least one number fits. Perhaps you want to try a little bit more, but this sound is promising. We also, by the way, have now also the initial conditions. Well, let's first describe what is the degree here. You see we have to go 2 back, so the degree is 2. Very simple. So how many initial conditions we need? Well, exactly these 2 would already suffice. Okay, so, but now let's solve this. So solve this equation, right? So r squared equals 3r plus 4, descending powers of r. That's why I put the an minus 1 first and then the an minus 2, that I don't get confused. Okay, so I have to solve now this equation, or rather factor this equation. So let me do it this way. So that would be r plus 1, r minus 4, I think, right? 2 numbers that multiply to make 4. Yes, that's correct. So we see that this minus 1 has multiplicity 1 and 4 has multiplicity 1. That means that the general homogeneous because this is a homogeneous equation, by the way, right? So homogeneous recurrence relation, an is equal to minus 1 to the power n, and put in front of there a general polynomial of degree 1 less than the multiplicity, that's degree 0, that's a constant, and that's the same there for the other one. So this is how it looks like, and we're almost there now because look, now we have to do the n is 0. We will know that a1 is then a0 is equal to where is a0? A0 was equal to 1, right? Because there was just one couple. So that's equal to alpha plus beta, and then a1 that was equal to 3, I think. Yeah, we had 3. a1 is 3, and that is equal to and now we take the negative, so we get the negative alpha and plus 4 beta. Let's add them up. That is 4 equals 5 beta. So we see that beta is 4/5. Right, okay? And then alpha, we can put it in here. So we see that alpha plus 4/5. Then we see that alpha is 1/5. Again, fractions, strange, right? Because we're taking the whole numbers and still the answer is written down in fractions. But I hope by now you have seen that this can happen. That these things kind of keep cancelling each other out. So an is equal to 1/5 minus 1 to the power n plus 4/5 4 to the n. Well, let's verify at least some of the numbers here. Let's verify that it works for 3 because we know the answer for 3. So if n is 3, what would it be? So a3 according to this would be 1/5 with a negative sign, because of the negative term, plus 4/5 times 4 to the third, that's 64. So if I would write this all out on 5, that is 256 minus 1 divided by 5, that is 255 divided by 5, that is 51. Holding my breath, yes, it's correct. Okay. So the next one is, the setup is a little bit easier here for the recurrence relation, so that's number 46. But the relation itself is a little bit more complicated, so let's read it again. So now we have these goats. Why not? They always have to be rabbits, right? Goats also like to procreate. And so we have somehow, we on the mechanism, how it works, we don't really care about. We say it doubles. Every year, the number of goats doubles. But we're goats, you want to do something with goats, and we're changing somehow a little bit what happens each month as well, is it, or each year? Every year, this goes by years. Goats take a bit longer before they start producing. Okay, so what happens is that, so 46A, the two scenarios, 46C is another scenario, is that as each year we import another 100 goats. Why we do that, we don't know, but somehow we are doing that. Okay, so can we write down the recurrence relation? Let's think about it. Well, the doubling is actually very simple. It means that the current amount of goats is just twice as much as the previous year. So an is the number of goats per year, okay? So an is the number of goats per year. No, the number of goats in year, in year n. Or after n years. Okay, but we adding each year 100. That's it. That's really what it is. So what we get, a non-homogeneous one. So now, okay, that takes a little time to solve, but luckily, what is the degree here? The degree is only 1, right? So it's going to make things much easier. Step 1. The homogeneous one is this one. And by the way, this is also going to make it easier for the next C, because we're going to have the same homogeneous relation, so we don't have to do the calculation anymore. This is R equals 2. Well, this is already there, right? So this means that 2 is a root with multiplicity 1. Okay. That means that an can be written as a constant, that's the degree minus 1 here, times 2 to the power n. So that's how the solution looks like. It's basically a geometric sequence. Step 2. what's the particular solution? Now we have to come up with a particular solution. And therefore we have to analyze the f. So f of n here is actually a constant, 100. So that means that the degree is 0 already. And then we only have to talk about s and its multiplicity. What is s here? Well, it will be now, I hope you are getting very much used to this. If you don't see a power, it means that it was 1. So s is 1. That's not a root of our polynomial, of our, of our initial, not a root of our recurrence relation, of our, of our characteristic equation. So m is 0. So we know how the particular solution looks like. Let me write it here. There's no power of n. D is 0, so that is just a constant, general polynomial constant degree times 1. So it's just a. Okay, it's just a, right? Alright, so what we do now is plug this in. Plug in, of course, in the original one. So we get a is 2a plus 100. This means that minus a is 100, so a is minus 100. So step 3. We know now that the actual number of goats is given by the general homogeneous one plus the particular one. The particular one is just minus 100. Yeah, minus 100. So, what do we need? Initial condition. So let's see. What is happening? Well, the first, let's see, the number of goats in the constructed recurrence for the number of assuming that during each constructed for the number of goats on the island at the start of the end here. I don't know what happens on the 0th here. The number of goats on the island, there are 2 goats on an island initially. Oh, 2. So now we are not counting pairs, we're counting goats, right? So really, so there were 2. So A0 was 2. That's what they tell us. If you interpret this as A0 was 1, okay, that's not a big deal. So let's make it simple, right? Now put n equal to 0 in this equation and we get 2 equals alpha minus 100. So we see that alpha is actually 102. And therefore, the number of goats at any given time is 102 times 2 to the power n minus 100. Okay, so let's look at the other scenario. In this scenario, so this is 46C, it's the same homogeneous part, we double, but each year we harvest, if you want, our goats and we take away n goats. Construct recurrence from the number of goats, assuming that n goats are removed during the nth year. Okay, that's what we do. So we subtract n goats here, and what is this? What is now different is step 2 and step 2 really, right? So step 1 is still the same. So step 1, we know that the homogeneous solution is still alpha to the n. Of course, this value of alpha might now be different. That is something else, but we know it's still of this form. So this is the homogeneous one. So step 2. Now we look at Fn. What can we tell about this? S, D, and M. I don't know why I always put it in this order, because it seems not really the most logical one. S is 1, right? Because Fn is minus n. Be careful, it's minus n, right? So S is still 1. D is now 1. That's the difference. And M is still 0, because we know that the characteristic equation only has one root, namely 2. Okay, so this means that a particular solution will look like this doesn't contribute. This is a general polynomial degree 1, a plus bn, and then s is just 1, so we don't have this. Okay, now we plug this in. We get a plus bn equals twice a plus b times n minus 1 minus n. Okay, not too bad. That is 2a plus 2bn minus 2b minus n. Okay, expand, I'll do expansion right away there. And so let's see what are the constants that we have here. So we have that, remember what we have to do is we put the constant term of this one equal to the constant term of that one. So a is equal to 2a minus 2b, or if you want, this tells, yes, so this tells me that 0 is equal to a minus 2b. And then we put this constant, the linear coefficient of the linear term is b, and here the coefficient of the linear term is 2b minus 1. Okay? And so from this we see that 3b is 1. No, not 3b. Sorry. b is 1. Okay, b is 1. And if b is 1, then we can plug this in. Then we see I minus 2 is 0, so a is 2. So the conclusion is this is a particular solution. A and b is 2 plus n. Now, is that the solution that we want? We don't know. We have to write down step 3. The most general solution will be the homogeneous one. Let me write it one more time, the formula, right? So it's the alpha times 2 to the n plus 2 plus n. And now we have to determine alpha with the initial condition. Now, we didn't look at the initial condition. Well, they told us, right? They said there were 2 in the beginning. Did I write it up somewhere? I said it, I think, but a0 is 2. Okay, so we plug in 0, so that is 2 equals alpha plus 2 plus 0. So, alpha is 0. And so this means, can that be? Yes, of course. So this means that the formula is 2 plus n. That, although, sounds a little bit weird to me. So let me double check here. So let me go back here. Perhaps n was 1 here. Oh yeah. So I have been misinterpreted the question. A1 was 2. In year 1, we have 2 goats. So we were counting the goats in each year. The first year we have 2 goats, and then new goats are born. So okay, we were off a little bit here with 1. So what we should have done is plug in n equals 1 in this equation, and so we get that 2 is equal to 2 alpha plus 2 plus 1, and so we see that minus 1 is equal to 2 alpha, so alpha is equal to minus a half. Yeah, they see here they have been removed only from year 3 onwards. I don't know exactly what they mean with that. So I find the question is a little bit vague in its initial condition here. But okay, so we find here, just following whatever this alpha minus half. So we see that the solution is a n is minus a half 2 to the n plus 2 plus n. I don't like this because this is gonna end up to be a negative number. I guess I have to take into account what they say, that there's only, we should start subtracting from n equals 3. Okay, so we should see what happens. A1, in year 1 there are 2, in year 2 there are twice as many, 4, and it's only in year 3 that we're going to subtract 1, so 4 minus 3. I guess that's what they mean then, right? Right. But it's still going to be, this not, I think the question is ill-posed, because look what happens in year 4 then. In year 4 we double, that would be 2, but we're subtracting 4. We're going to get negative numbers of goats here, which is of course not possible. I wonder, or perhaps, okay, sorry, as I said, there is not very clear in the way that they started thing. Perhaps they mean that is 0, in year 0 we have 2, so in year 1 we have 4, in year 2 we have 8, and only then the next year we start subtracting. So there's a 16, 2, 4, oh no, I was already wrong here, right? I forgot to double here, so this should have been 8 minus 3, that is 5, sorry, that is where I went wrong here. So that's the 8 minus 3 is 5, then we double, that is 10 minus 4, that would be 6. in year 5 we would, what do we do? Double, so 12, and we subtract 5, that would be 7. Okay, so our initial condition therefore is we have to start here with sorry, the formula starts from year 3, they say. Okay, so for this, so 5, we have to start with 5 for n equals 3. So 5 is equal to alpha times 2 to the third, 8, so we do n is 3, right? Plus 2 plus 3, so that's 5. No, I can still get alpha is 0. I'm sorry, their initial condition is very vague. They should have told us something more concrete here. So I guess it is what I was saying. In 0 there is 2. No, I mean it should be working too with this one. Okay, depending on what exact initial condition was, so let's assume that initial condition would have been, let's see here, in year 0 there would have been 2, in year 1 there would be double, in year 2 there would be even double, in year 3 there would be even double, but now subtract, so that would be 13. Okay, so let's see what that gives me. So I'm now using n equals 3, that is 13 equals alpha times 8 plus 2 plus 3, right? So I'm plugging in 3 in this equation to calculate A3. And so I think this now gives a little bit more, this comes now out a bit nicer. So this is 5, so this 8 is alpha 8, so I see that alpha is 1. So the number would be therefore 2 to the n plus 2 plus n. That sounds a little bit better of a formula, at least it's positive here. We don't lose goats. Negative goats that start reproducing, I don't know what that gives. All right. But this is the issue that we had a little bit at the end is an issue of initial conditions, and I always make sure that the initial conditions are extremely clear, that's not in debate here.